Morning, all. All right, again, we are continuing with module 3. All right, and we've reached X-rays. Last day, all we did was look at how X-rays were produced. Um, we looked at the specifics about X-rays, and as you realize, you really and truly had no idea about anything regarding X-rays other than we use X-ray machines to look inside of somebody. Right? When you think about it, you knew absolutely nothing about X-rays, which is kind of you sit down and scratch your head, like, yeah, boy, I know nothing, nothing, nothing. But we went through that. We looked at how X-rays are produced. The method by which X-rays are produced are the complete opposite to the photoelectric effect, which was kind of ironic. And there, we know that there are different types of X-rays, right? And how we get different X-rays depends on the radiation or um, the electrons that are hitting our material. Is exactly the same kind of concept as photoelectric effect, as you realize. So we're going to go on to X-ray spectra, because X-rays we look at we don't just look at the universe and look at things with using visible light. You all know that we use infrared, we use radio waves, as we have the big radio telescopes to read radio waves. We use microwaves to communicate, phones and whatnot. Right, infrared heat signatures. We can read infrared heat signatures everywhere, visible light, UV. And we do also have a spectrum of the X-ray, an X-ray spectrum. And we can use the X-ray spectrum to determine how much energy is being given off by a certain atom. So we do have X-ray, not on Earth, but we have X-ray telescopes essentially in space. We have the Chandrasekhar X-ray telescope that's meant to take photos of the rest of the universe using the X-ray spectrum. Now, the X-ray spectrum is usually given off by black holes, right? Really, really high energetic systems. So that's how we are able to determine where black holes are and whatnot and look at their interaction. So we do have telescopes that use the X-ray spectra, right? When we go straight up to gamma rays, right? So here you didn't even know that, wow, we have X-ray telescopes. Things out there in the universe give off X-rays, right? Here on the Earth, we know how to produce X-rays. So obviously, if it's part of the electromagnetic spectrum, we can use it just like light. So let's read from our screen. Where'd my pen go? Just hold it. All right, so just going down to our X-rays. So continue with X-ray spectra. Let's read from the screen. X-ray spectra. The energy of a photon, of a light photon, is a few electron volts. Remember, we did cover what electron volts are. They're basically the energy at very, very small energies. If you want to run it through, 1 eV is essentially 1.6 by 10 to the minus 19 joules. So the energy of a photon of light, as in light, visible light, Roy G. Biv, is a few electron volts, while the X-ray photon is several kilo electron volts. So this means that an X-ray photon is a few thousand times more powerful or more energetic than light. So X-rays are able to penetrate far into the atom and displace electrons from deep energy levels. Remember, this is in atomic physics, the entire story is in the atom and more uniquely closer to the nucleus, as our entire story lies. So what happens when we have an atom and we have our nucleus? Depending on how much energy you have, a wave can penetrate certain depths in an atom. So it depends on your energy. And how do we determine energy of an electromagnetic wave? E is equal to HF. So your frequency makes a difference. And the thing about X-rays, because X-rays have a lot of energy in them, they're the second most energetic type of wave that we have. They are able to penetrate deep within the atom to the point where they can displace or or excite electrons way down into your first shell, right? To get to your first shell is hard because remember that first shell is bound really, really closely to the nucleus, right? We have that whole big positive charge, that ball of positive charge in your nucleus, and we have two little electrons sitting next to it. Man, that's the strongest electron force in the universe, right? Electrostatic attraction is the stronger, nuclear attraction is the strongest force in the universe. So the fact that an X-ray has enough energy to cause those electrons to be excited, we can get an X-ray spectrum diagram or ladder like we did the other day. So the fall of an electron from one level to another causes the emission of high X-ray, high energy X-ray photons. So this is how we get X-ray photons. Energy goes down straight into the atom, right? Straight down probably to your level one, your first shell, your second shell. And to get an electron to get excited from those shells and then move up, right? They move up and then they fall back down. They will emit an X-ray, right? So let's continue reading. The K series of an electron-like spectra is when an electron is knocked out of its lowest state. The lowest state possible is the first shell. All right, your first shell, which is the shell right above your nucleus, that's your first shell. So that means you're talking about a lot of energy. If this is your nucleus, that's your first shell. What's your first shell? N? Chemistry people. What's the name of your first shell in an atom? Anybody but Andy. Any? Barry, give me an answer.
I remember that. As I can remember that.
People who do in chemistry, what is the first shell in your atom called? What is the letter allocated to your first shell? You can put it in the chat too. Come on, folks.
She'll go for the answer, right?
Tila.
Miss, I do remember.
Gerard.
It's not S.
S is your first shell?
Can't remember.
Like that way, I mean, Miss?
Yeah, what's your first shell in an atom?
Yes, the S and then the P.
SP. What else? Oh God, I only remember the first two. All right, so that's your S shell for chemistry students. This is something you all should know from CSEC. All right, if that's your nucleus, your very first shell, which is your S shell, your next shell, which is your P. Remember in your S shell, you only have 2 electrons in it. Everybody here would have done chemistry at some point. Remember, your P shell has 8 valence electrons. So the fact that energy that is needed to move these 2 electrons is very, very large. All right, so anytime we move these 2 electrons and they get excited, meaning they go up to next energy level and they fall back down, chances are they could emit an X-ray photon of energy. So let's see, when an electron falls through one level, we get an alpha series. So K series, we have a whole bunch of different series of or types of X-rays. Types of X-ray, remember before we had talked about, we had hard and soft X-rays, where we had soft X-rays, the one that are able to penetrate flesh, and hard X-rays are those that can penetrate more solid matter like concrete and steel. Right? Obviously, softer X-rays are those that don't have as much energy. Hard X-rays are those that are able to penetrate deep into a material. Now here we're going to go even a little bit more. We have different levels of X-rays, and we could determine how much energy it has just by looking at which level of the atom, which level within the atom that X-ray came from. Whether it came from, right, if this is your N1 shell or your N1 level 2, 3, 4, when it falls from one particular level to another, it's going to give off an X-ray of a certain type. It's going to give off X-rays of certain numbers. Hold on, y'all. Right? So let's look. So we have three type of X-rays or X-ray spectra that we can get. Remember, we said we can look at how the X-rays move. The X-ray spectrum works just like how we have visible light. We have a spectrum of light. You know, Roy G. Biv is a spectrum showing us different wavelengths of that light or different frequencies of that light. Similarly, for the X-ray spectra, we have different levels. We have the K, L, and M series of X-ray waves. All right, so let's read the K series. Whenever we have the K series goes straight down to your lowest level possible. So these are obviously the highest energy X-rays that we have, because to get to your first level, that S shell, you take a lot of energy to displace those very, very, very tightly, strongly bonded electrons in your atom. Remember, we're not ionizing our atom. We're not doing that as yet. We're just exciting our electron to go up from one level, you excite it, and then it's going to drop back down and emit some form of electromagnetic wave. That is how it works. That's how you emit all electromagnetic waves. We excite an electron. It's that simple, folks. We excite an electron, it moves up a shell, then it drops back down, and it emits some sort of radiation. Please note, radiation is not always nuclear radiation. It's that simple. That's how we get everything. Just electrons doing what they have to do and get rid of excess energy. Universe is not complicated. So our first type of X-rays, which is the most powerful ones, are the K series. The K series are the electrons that fall down to your very lowest level, closest to your nucleus. And then we have four types of K series. We have alpha, beta, gamma, and delta. That's delta. This simply indicates which level it falls from. Alpha is when it falls from, let's see, from level 2 to level 1 will be alpha. From level, let's read here, from level 3 to 1 will be beta. Level 4 to level 1 will be gamma. Level 5 to level 1 will be delta. So all we have to do to look at to know what kind of X-ray we're looking at, we can name it. So if I know I have a K alpha spectrum, I know that that atom has dropped from the second level to the first level. That's all it says. So you already know what kind of process is happening in that electron and in that atom that is giving off the X-ray. So pretty cool, you know, they have it labeled. They have it labeled very well. And alpha, beta, and gamma actually basically going to tell you how many levels it dropped from. Alpha means one level. Beta means two levels. Gamma means three levels. So let's keep that in mind when we look at the other ones. So we have here the L series. The L series is not as energetic as the K series because it's only falling to not so deep level. All right, it's not going down to ground level, which is your closest energy level or the closest atom electron level to your nucleus. Let's zoom in a bit here. This looks a wee bit small. So for your L series, remember we said, sorry, my apologies, folks. I don't know why it does that. Right. So I have here alpha series. Alpha series means that it only falls by one level. Beta series means it falls by one, two levels. And then gamma series means that it fell through three levels to go where it is going. Similarly for M, your M series is not as energetic X-rays. All right, so probably M series is a soft X-ray. Probably. If you think about it, it'll be a soft X-ray because the amount of energy it takes to fall from one level, from a high level to not that high level, is not that much. But the energy it takes to fall straight back down to ground level is a lot of energy. So all you have to remember, alpha, beta, alpha, beta, and gamma simply tells us how many steps we fall down. Alpha is 1, beta is 2, gamma is 3. Then you have K, L, M. These tell us the series that we're looking at. The K series in your X-ray spectra falls down to level 1. L series falls to level 2, and M series falls to level 3. So you get a whole range of all your X-ray spectras. So you already know what type of energy you're looking at. There's a general range for these energies when we are given a spectra. So let's see what this looks like in a graph, because what is physics without a graph, folks? So let's see. The typical spectrum of X-rays has two distinct components. One, it has a background of continuous radiation, the minimum wavelength of which depends on the operating voltage of the tube. How are X-rays formed? We take a high-speed electron, we accelerate a high-speed electron and we fire it into a particular material, into a particular metal. That metal absorbs that electron. It causes all the electrons in that metal to get excited. And of course, they're going to fall back down and emit an X-ray. That's basically what it does, right? We take an electron, fire it into a metal. That metal is going to absorb the energy, and all of the electrons here are now going to get excited, right? And it's going to be enough energy to make them excited, but not to cause ionization. Right? Ionization is when we cause the electrons to leave the metal and become a free electron. That is not what is happening here. You're given just enough energy to cause excitation, and when your electrons have become excited, they're going to jump up to another energy level. And then because they didn't reach ionization level to become free of the atom, they're going to fall back down to where they came from. And as a result, they will emit an X-ray photon. Simple, that's all it is. And the wavelength or the amount of energy these X-rays have obviously depends on the energy of that electron. Y'all, this is simple physics now. If I hit these electrons here with a very low energy electron, that means there's less energy for them to absorb. All right, using the law of conservation of energy. If I use a low energy, right, and how do we get energy in electron? We use a high voltage or we use a low voltage. See how all your physics is going to come into play now? As in all. Right? So when I have a low voltage, I am not putting a lot of energy into my electron. So that means when that electron hits your metal, not that much energy is being transferred to your electrons. So that means they're not going to probably move from the K level. They're probably going to be a L or M level electron, M level X-ray. Now, if I use a high voltage, that means I'm giving a lot of energy to that electron. So that lot of energy means that as it hits that metal, as it hits the metal here, it is going to transfer that high energy to these electrons. So these electrons are going to, number one, have more energy to excite the electrons. So not just the outer shell electrons will get excited. That means the lower shell electrons, the ones closer to the nucleus, will also get excited. And if they get the lowest shell electron excited, that means they're going to rise up, all right, go up to other energy level. Remember, you want another energy level to close to ionization. And because it's not getting enough energy to be ionized, it's going to fall back down and then emit an X-ray. That's all they do. So it depends on how much energy or what is the voltage being supplied to your X-ray tube. We can get different types of X-rays, different wavelengths of X-rays, different frequencies of X-rays. Please note that wavelength and frequency here is interchanged terms. They're going to use both terms meaning basically the same thing, because please note that we still do use C is equal to F lambda. You see, C is equal to F lambda and E is equal to HF is our foundation equations for this entire topic. It's always in the background of our minds to use them. So please note, when your frequency changes, your wavelength is also going to change in a predictable manner or in a linear manner and fashion. So this is why we look at the wavelength of the X-ray. We can look at the frequency too, because it's the same thing. All right. If your wavelength goes down by a certain amount, the frequency is going to go up by a certain amount. But here we look at wavelengths, and we have a minimum wavelength. Right? So we have a minimum wavelength, and this is when we have the smallest possible, or it depends on the voltage of your tube. So what is our continuous radiation? Our continuous radiation is this curve. Just the smooth curve, if you have a graph, this smooth curve is your continuous radiation. This is the continuous set of X-rays that are given off all the time. And then we have a few intense emissions at a few discrete wavelengths, and this is called the X-ray line spectra. Remember, we did line and continuous and band spectra the other day. All right, so X-rays do have a line spectra, and what the line spectra does, these are little peaks and little spikes um, in your radiation or in the energy being given off that correspond with the energy levels being crossed by your atoms or your electrons. So the wavelengths are characteristic of the material and are independent of operating voltage. So this is something interesting. Remember we told you, or you went through last day, that each material has their own specific spectrum, right? Meaning they have their own specific spectrum, their own specific energy level diagram. Similarly here, each metal, right? Each metal has their own specific line frequencies or line spectra. So each metal, depending on the kind of metal we use to create the X-rays, we don't always use the same metal. You all can read it up, right? We use different metals to create different X-rays. So this is the general X-ray produced as a result of simply the electrons interacting with your metal. Now, each metal is going to have an energy spike, right? And these energy spikes are going to tell us which level our atom is dropping from. So just look at why we have two curves here. One curve is actually going to show you what happens when we have a high voltage, and the next one is when we have a low voltage. So when I have a high voltage, all right, when I have a high voltage, I will have my continuous spectrum as you all see here. And then I'm going to have a high peak for my K alpha. Why will I have a high peak for my K alpha? Because K series is the most energetic series. And alpha series means you're dropping to the first level. You're dropping from one level, from the second level to your first level. So that's a very high intensity wave. Then we have the right after that, we have the K beta series. K series is still the most energetic one, hence why it's at the top of the curve, because it has the most amount of energy, the highest intensity of your X-ray. And then we'll have the beta. Then we're going to go down the curve, and you're going to realize afterwards we will get to L. And of course, with the L, we're going to have alpha and beta. Depending on the material, we could have all. If you all look online, you're going to see we have some with a whole bunch of peaks all over. And further down, depending on the material, you'll probably get an M series. So this is what it looks like. You have your continuous radiation being given off, but owing to the metal itself will give us a few little peaks that help us identify what material it is. Now, as I said here, let's read this sentence again. The wavelengths are characteristic of the target material and are independent of the operating voltage. Now, once we have the voltage or the amount the electrons have enough energy to create an X-ray photon, we will get our peaks happening at the exact same point. So this is when we have low voltage, this is when we had high voltage, and if you look at that, our peaks still occur at the exact same point, the exact same wavelength. So here, all we're doing when we use a higher voltage, we're just giving our electrons more energy, right? But they will still give those peaks at the exact same point because those are indicative, right, of the metal itself. All right, so the nice thing about these graphs, they one, tell us what is the minimum. Lambda min is the minimum, is the wavelength where all the X-rays lose their energy at once. Remember, in this topic of quantum physics and whatnot, we have instantaneous actions. We have instantaneous events, and this is also one of them. Right? We have a particular wavelength where all of the energy stops because that's where we go from X-ray to probably UV. So we don't have enough energy to produce an X-ray. You need a certain amount of energy to produce X-rays, right? And when you drop below that certain amount, we stop producing them. So here we have lambda min is simply the wavelength at which all your X-rays lose their energy at once, as in they just stop working, they fall down flat. All right, so here you're able to identify what your levels are, where your atoms are moving in your, where your atoms or electrons are moving in your metal. So you can determine when you have K, alpha, beta, and gamma series, when we have L and M series. Usually in this question or when you have exams, all they're going to ask you to do is to explain this graph. One, explain the continuous graph. The continuous graph is just simply the X-rays being produced by the machine or by the process. And the peaks here are indicative of the metal being used to create your X-rays. All right, and please note that once we have enough energy to cause an X-ray to be emitted, hold on, record. All right, so let's continue on. So again, as we said in exams, all they're going to ask you to do is explain these topics. It will come for multiple choice and it will come for the long paper. You remember we get in exam topics in a couple weeks. Hopefully it's usable topics. X-ray absorption spectra. Now we have emission spectra and we have absorption spectra. Because when you emit energy, that's an indication that you're absorbing some energy. Can't have one without the other. So let's read, or let's get rid of this white pen. All right, so X-ray absorption spectra. In a monochromatic beam of X-rays, now monochromatic is a monochromatic indication of color. Anybody?
Yeah.
Yeah. So do X-rays have color? X-rays do not have color. So what do you think they mean by monochromatic beam of X-rays?
Well, one is one. So one.
It, we probably can see it, I guess. I don't know.
We can't see X-rays. Anyway, monochromatic means that we're looking at one, oops, that we're looking at one, why am I writing this wrong? At one wavelength of light or one wavelength of X-rays. Remember, we did say that we have a whole range of X-rays. We have a whole set of different frequencies that an X-ray can be emitted at or can exist at. But here we're going to look at one frequency or one wavelength of X-rays. That's what monochromatic in this stage means. Even though we usually say chromatic to mean light, you know, just as we're saying, we're using light as a general term for any sort of electromagnetic photon. Right here, monochromatic simply means we're using one wavelength of X-ray or one frequency of an X-ray, one specific one. We're not using a whole range of them. Kind of like, remember when we were doing um, interference and diffraction, we needed one wavelength of light, otherwise we'd have gotten a whole bunch of interference happening. Remember that? That's why we have to use one wavelength of light, or we have to split our light to get identical waves. Similarly here, we need to have one identical type of wave for your X-rays. So monochromatic means one wavelength or one frequency. So in a monochromatic beam of X-rays of intensity I naught, right, of intensity I naught. I naught, you all know anything with subscript naught means initial value, starting value, or value at time zero. All right, so of intensity I naught, incident on an absorber of thickness X, the intensity of the emergent beam I is given by the equation I is equal to I naught e to the minus mu X. So let's see what that equation actually is talking about. We all know X-rays are used to peer into a material. So obviously that X-ray is able to penetrate into a material. Some goes in, right? Well, all of the material goes in, some of it is going to get absorbed, and then some pass through the material. That's what X-rays are. All right, that's what we use them for. So let's look at it here. We have an object, all right? It has a thickness, it has a particular thickness, so the thickness X, right? We have an X-ray of a certain amount of rays coming in. Now, as the X-ray passes through the material, more and more of those X-rays are going to get absorbed by the material. So the thicker the material, the more those X-rays will get absorbed, to the point where only some of them will come out of the material. So if I had a very, very thin material, let's look if we had used a very, very thin material. All right, so suppose I had used something this thick. Let's go in a wee bit more. Suppose I had used, sorry, stop moving. All right, suppose I had used a material this thick. Then that means of my incident radiation, this amount of my X-rays would have passed through. All right, so the thicker the material is, the less of the X-rays or less X-rays will penetrate the material. So here, how much a material can allow X-rays to pass through depends on several things. One, it depends on the material itself. All right, so here your atomic number Z. So as you go down the periodic table, they are able to absorb X-rays better and better and better. All right, and then we have the thickness of the material. That's simply all that tells us whether or not X-rays can pass through material. One, their density and where they are in the periodic table, and their thickness. So if I have my incident radiation I naught and my resultant or penetrative transmitted radiation of I, how to work out I from I naught is a simple equation of I is equal to I naught e to the minus mu x, where mu is your linear absorption coefficient of your material. This is unique to every single material, and it depends on their density and where they are in the periodic table. The units for linear coefficient, linear absorption coefficient is m to the minus 1. And remember here, x is your thickness of your material. Please note that this must be in meters in order to cancel out your per meter. So it's a really simple equation, all right? Anybody want to make a guess why I have a negative sign here? Why do we have a negative sign in an exponential equation? To indicate what? That's an easy question. These are exact questions from exams. They will ask you, why do we have a negative sign? Anybody want to give it a try? Minus means what in maths? What happens to a number when you minus something? I see a chat. I see shy people. Jabari, sit down. I am laying out very, very simple to you all.
Okay, minus means to take away in maths. Yeah,
Right? And what happens when you minus something? What happens to your general number?
it lessens.
Decreases.
It gets smaller, right? So a negative sign in an exponential equation means that we have a decrease happening, all right? So this is what we're going to end up knowing. This is how we end up knowing that we have a decay curve. Anytime we see a minus sign in an exponential equation, we know we are dealing with exponential decay. And here we can see as the material gets thicker and thicker and thicker, your incident or your radiation gets smaller and smaller and smaller, which means it is decaying or getting less. Right? So that is, please, please, guys, girls, my wonderful upper sixes, a negative sign does not mean it's negative alone. A negative sign in exponential equations means you have a decrease curve. You are going to get a decay curve. So this is your decay curve, and when you have to plot a graph of this, a straight line version, you are also going to get a negative line. You're going to see this. We already did it in the half-life lab. This is extreme. This is exactly the same kind of process as in the thicker the material, the less X-rays get through. So you're going to have a decrease in the number of electrons the number of X-rays we are working with. All right, so let's go down. Mu varies with wavelengths, right? Obviously, mu is going to vary with wavelength. Mu is oh, mu is your absorption coefficient. Some X-rays can only travel a certain distance in a material, right? As we did for soft and hard X-rays. Some can only travel a certain distance into material. Like for soft X-rays, they can only pass through soft waterborne flesh. They are unable to pass through bone. But if I use a wavelength or an X-ray with a smaller wavelength, which means it has a higher frequency, C is equal to F lambda. When your wavelength gets small, your frequency gets large. So if I use a wavelength, a bigger wavelength and a smaller wavelength, it is going to tell us how far it's going to penetrate into your material. So you see, using X-rays is a complex process because it depends, one, on the energy of the X-ray. Each X-ray, depending on the energy, can penetrate further into an atom, right? And then we have certain atoms, depending on their element and their density, will allow X-rays to only pass a certain distance. So mu is a little complex topic to work with. To determine mu is complex. You're not supposed to know it right now at all. Even into university level, I don't think we even touched mu for more than one half of a session. So mu varies with wavelength and is sometimes necessary to express I in linear form. Of course, we have to express I in linear form. Why would we ever use curves in mathematics and physics? We use straight lines, right? For joy. So we have here I is equal, this is our straight line version, I is equal to I naught e to the minus mu x. This is going to give us our nice curve. We can't do anything with that curve other than read off a value at different points like your half-life curve. You can't work out a gradient, you can't work out a proper intercept because the intercept here might be flawed if you're using a best fit curve. You can't do anything too productive with it. So how do we plot a graph? We must get a straight line graph. And what is the reverse of natural log E? We take ln, right? Ln is the reverse of natural log E. So you take ln on both sides, right? You take ln on both sides, so you're going to get ln I is equal to ln I naught e to the minus mu x. I'm showing you the entire length. Exams are coming up and make sure you get it. You can remember when we have multiplication in any sort of indices and whatnot, multiplication means addition. We can split it up and add it. So this is going to be ln I naught plus ln e to the minus mu x. And the way it works with indices, when you have an index, you can bring it in front, you can multiply it and bring it to the front of your number. So you're going to get ln I naught minus mu x. Why? Because minus mu x by plus is a minus number. All right, really take my time and breaking this down for you by ln of e. Now ln of e works out to be 1. Ln cancels e perfectly to give us 1. So 1 by any number is the same number. So if I wanted to put this in linear form, ln I is equal to ln I naught minus mu x. And that is your straight line graph if you had to find out or to work out any sort of topic or any sort of value in X-rays when X-rays are penetrating into a material or when they're passing through a material. We're going to use this equation of ln I is equal to ln I naught minus mu to the x. Please remember, I have taught you all how to identify your topics or your terms in a straight line equation. When we have a straight line equation, y is equal to mx plus c. Remember, m is your gradient, x is your manipulated variable, right? C is your y-intercept, and y is your responding variable. So if you look here, let's think about it in simple terms and topics. If I were to increase my thickness of my material, right? Let's just use simple knowledge here, simple common sense here. If I had a thicker material, this is my intensity, ln intensity. If my material gets thicker, that means the intensity of the radiation coming out of that material will get smaller and smaller and smaller because the more material that X-ray passes through, the more of those X-rays are going to get absorbed by the material. So that means our intensity of our radiation coming out of your material or penetrating through your material will be smaller. So obviously you should get a negative graph when you're doing this topic, right? Everybody sees why we end up getting a negative line. You're supposed to get a negative line when you're doing this because common sense, let's use common sense. Sometimes you have to sit back and look at something simply because there's always a simple explanation for everything. Well, beside quantum mechanics, that's just craziness. All right, so everybody understands here how to read this graph and how to analyze and rationalize this graph. The thicker your material gets, the smaller and smaller your intensity is going to get. So that's how we end up getting a negative graph. The negative graph indicates we are decreasing in value. A positive graph always means that we are getting larger. Right? A lot of students still don't wrap that around their mind for some reason. But let's get it out now. Because you have two topics in Module 3 that deal with decay curves. Those are X-rays and radioactivity half-life. Right? Exact same behavior. Right? As in they have decay curves, they get smaller as time passes, and you have to be able to identify why that happens. All right, so let's look at our graph. So when we have our graph, so you all can see why your X is your manipulated. So X is your manipulated variable, because as you change X, your intensity is going to change as a result. And let's see here, your y-intercept is your C, and your gradient will be your mu. Please note that your gradient here will be negative because it indicates that we have a decrease in our intensity as distance increases. So that's going to be it for X-rays. Let me see. We could do the Broglie equation, wave particle duality, and then we'll stop there because we have about a... No, actually class is finished. All right, so we will stop here. Save that. So we'll stop right at X-rays. And then what do we have left for the syllabus? As in this handout is the rest of the syllabus. All right, we have wave particle duality. That's scrolling through. We have nuclear energy. So wave particle duality, nuclear energy, you all can see is not, is looks like plenty, but it's not really. All right, we have nuclear energy, a lot of diagrams, a lot of pictures. This is not the printer safe handout. All right, so we have all of these we're going to finish the next day. So we're going to do wave particle duality. We're going to do nuclear, nuclear energy, fission and fusion. That is our next day class. And the class after that, just to tell you where we are, the class after that will be to deal with decay law, half-life, and that's it. All right, so we have 2 more lectures for the syllabus, all right, which will be next week and probably a little bit more. All right, so after 2 lectures, we are done. Then we're going to sit down and do some questions regarding module 3. All right, so I actually do have a couple sessions ready for you all for that. So that's where we've reached. Let me stop the share. Pull this across here, and let me speak to you all about moderation and me being here in class. All right, so I do have moderation. I'm looking for my schedule, sorry. All right, I do have moderation from Monday. All right, so I am going to be out for quite a few days, but because we all have 2 recorded sessions left, I am going to leave. I'm going to pre-record those sessions and put it up for you. All right, so you can look at those sessions. Oh, sorry, dog is inside. Hold on, you all. Right, so those 2 classes, if I can't make it to class, all right, because I will have moderation next week. When is the 4th? Do I have you all out on the 4th? On the 4th, we will have class, all right, because I have a school in Sangre. I need to moderate Monday, Tuesday morning. That's when I have class with you all next. All right, we have last period, so that means we will have a live class for that. And then the class after that, which will be on the 10th. So we're going to have 1 class. I will post up that recording beforehand so you all can look at it. So you only going to have one more recording classes or YouTube class to finish up the syllabus. So we will have class next week Tuesday because I will be finished with my school by lunchtime, right there in Granny, so I'm not going too far away. So we will have class on Tuesday, and the class after that will be a recorded session. And then after that, we're going to have work sessions. We're going to have tutorial sessions. If I have a moderation that coincides, I will have to pre-record that also. So please, folks, do your questions when I start posting tutorials, and we're going to finish this up, and then we're going to start discussing um, general revision. So basically, we finish the syllabus next week. All right. So let me